everyone. This project aims to accelerate California's transition to zero-emission vehicles. We are UCLA Environmental Science students in partnership with the Union of Concerned Scientists. The impact of tailpipe emission from older gasoline and diesel vehicles contribute greatly to air pollution and negative health effects, and are disproportionately distributed across the population. Our goal is to identify key areas where there is a higher distribution of vehicles older than 2003, and gather findings on their impact on air quality and health effects. We hope our analysis can serve as a guide for policymakers when it comes to disadvantaged areas inequitably affected by vehicle pollution. Our research is broken down into 5 subgroups: vehicle emission, air quality, health effect, and environmental justice. This is a roadmap of our research process. The vehicle group obtained the data from the California Air Resource Board, or CARB. We set 2003 as a boundary year to differentiate between older and newer vehicles. We have determined and mapped out the distribution of pre-2003 vehicles and generate shapefiles for subsequent groups to use. Figure 1 and 2 show the distribution of older vehicles across California at the county level and across LA County at the tract level, respectively. Figure 1 uses a log scale and Figure 2 uses fractions of total vehicles. This map aims to assist the future policies targeting regulation in areas with denser older vehicles.
The emission group obtained annual average emissions in 2019 from MFAC, an emission inventory website by CARB, to compute emission rates, and have joined them to the vehicle dataset to compute emissions of pre-2003 vehicles. This will help us visualize the distribution of emissions by pre-2003 vehicles across California. Both figures here compare vehicles model year and corresponding total PM2.5 emissions from 2019. Specifically, figure on the left shows emissions from vehicles made in 2003 and earlier. Figure on the right shows emissions from vehicles made in 2004 to 2019. Based on these figures, a large portion of emissions are from vehicles made in or before 1973, and emissions seem to continuously increase in vehicles made after 2010. Although further analysis are needed, we hypothesize that the higher amount of emissions from vehicles made in or before 1973 and after 2010 are because there are a higher number of these vehicles and not necessarily because these vehicles emit more emissions. Next, we plan on checking for more correlations between vehicle characteristics and emissions due to mobility prioritization in policymaking. We're also investigating fractions of households with only one vehicle and the fractions of emissions that can be saved if all of their vehicles were replaced by zero-emission vehicles. Additionally, we are researching the cost of removing each ton of pollution. Lastly, we have formatted and passed the emission data set onto the next group for air quality modeling. The air quality team is using InMap, a tool that simplifies modeling air quality by taking the annual average of meteorological conditions. We've tested the model using various datasets to troubleshoot for any errors in the simulations. We've also run simulations with the official emissions obtained from the emission team at various resolutions. Both figures here show resulting PM2.5 concentrations in micrograms per cubic meter by emissions from pre-2003 vehicles. These concentrations include both primary and secondary sources. Figure on the left shows significant PM2.5 concentrations in LA, the Bay Area, as well as some parts of Central California. Figure on the right is a zoom-in area of figure on the left in the LA region. We will also be zooming into other specific areas of interest for analysis at a finer scale. These air quality results have also been passed on to the health effects team for further analysis.
The health effects portion of our research aims to find out the health impact of older vehicles by testing a hypothetical scenario in which all vehicles older than 2003 are removed. We used air quality modeling outputs and the BenMap modeling system to map the health effects difference between a baseline business as usual scenario and a control scenario to show mortalities that could be avoided if action were taken to reduce older vehicle emissions. We've modeled mortality at a 4-kilometer resolution statewide and 1-kilometer resolution for LA County, and are now working on the air quality regions of the South Coast, San Joaquin Valley, and Bay Area. We'll also create results for asthma incidents and hospitalizations. We'll then aggregate our final statewide results by county, and from there we'll estimate a cost related to potential loss of life using the estimated statistical value of life. Figure 7 shows the annual increased death per 4 kilometers, while Figure 8 shows a 1-kilometer resolution for LA County. This is based on an EPA standard health function by Krusky et al. 2009. The total avoided deaths from removing older vehicles would be over 1,500 avoided deaths for the whole state each year, and almost 100 deaths avoided in LA County alone.
So far, the environmental justice team has used ArcGIS to map socioeconomic data such as racial distribution and the ratio of median income to federal poverty. Next, we plan on devising a formula that integrates older vehicle distribution, emissions, air quality, and health effects. While it's important to look at where older vehicles are located, such a formula will allow us to factor in other aspects that play a role in vehicle emissions pollution, such as topography and the age of vehicles. Then we will map the calculations and compare it to racial and income distributions to highlight vulnerable communities that should be prioritized, as they would benefit the most from the transition to zero-emission vehicles. Figure 9 shows the density plot of Hispanics and Latinos and older vehicles at the block group level under the condition of 1 vehicle per household. We can see a positive trend where as the fraction of vehicles older than 2003 increases, so does the fraction of the Hispanic and Latino population. We found that there was a higher correlation in Hispanics and Latinos compared to other races. Figure 10 shows a comparison of air quality due to emissions from pre-2003 vehicles in PM 2.5 concentrations of micrograms per cubic meter. These values were derived from the sum of PM 2.5 concentration from older vehicles for each census tract, weighed by the population of each racial group in each tract. We can see that African Americans, Asians, and Hispanics and Latinos experience the poorest air quality. These two maps compare air quality concentration levels of PM 2.5 in micrograms per cubic meters to the distribution of Hispanics and Latinos, African Americans, and Asians. The map on the left is focused on the LA area, while the map on the right is focused on the Bay Area. In the LA area, we can see that Hispanics and Latinos are exposed to poorer air quality, but in the Bay Area, Asians are exposed to poorer air quality. Additionally, our team is performing outreach to share our findings and analysis across a wide spectrum of those working on air quality issues. Several organizations and people have been selected to contact. Among them are groups like advocacy organizations and policymakers.
Here's a summary of our progress and where we stand in our research currently. As our project comes to a close, we hope to share our findings with relevant decision makers to promote policies that phase out older vehicles and help California meet its emissions goals in alignment with the aim of the Union of Concerned Scientists. Thank you for listening to our presentation.